Yeah, let's start then.
Yeah.
Yeah, so this is going to be focused on just circuit building. So if you're into ZK cryptography or anything else, yeah, we're not going to cover all of that. So our main characters for this session are going to be Alice and Bob, and we'll go through a bit of zkSNARKs and then dive into Circom and Noir. So just to get into the zkSNARKs part, Um, so how did this all start? So let's say Alice has a secret array of 8 alphabets and she wants to check if Bob has the same secret. So Alice could do one thing. So Alice could go to Bob and say, "Hey, just let me know what is the second letter of this secret." And Bob could say, "Yeah," like Alice could say, "Is it T or is it H?" And Bob could say yes or no, and hit or miss. Bob might get a few answers right, and Bob might get a few answers wrong. And in this process, the secret is gonna be leaked. So you're actually giving Bob the letters, the secret. And this is not really an efficient way of communicating, passing secrets, I would say. Or the second way would be to say, "Hey, Bob, just send me the hash of the second alphabet." And Alice could compute the hash of the second alphabet, which is T, and Alice could see if the hashes match each other. This way, we don't leak what the secret is, which is a more efficient way. And if you just want to see how the story ends, just refer to Justin Taylor's first chapter, which is in his book Proofs and Arguments. So this is how we start the ZK snarks problem. What we just did, the second approach to this problem is that we hashed the secret, and we talked to Bob. We uh, we were in a conversation with Bob to see if we have the same secret or not. And this process can be now divided into two parts. So the part one is going to be hashing of alphabets, the secrets, and part two is going to be interaction with Bob. And again, um, this is just a layman's description of what ZK snarks or anything is. And if you want to watch more about this, you can go through the MOOC lectures which were released in March. So the hashing of the alphabets, we have a message which we're going to turn into polynomials. So if you're new to this, just think message is going to be 1, 3, 4, and to turn it into a polynomial, you're just going to do x squared plus 3x plus 4. And what we do is we multiply coefficients with random numbers and squares of random numbers. So this especially is called a polynomial commitment scheme. This is very close to hashing. So there are cryptographic commitment schemes, there are cryptographic hashes, but commitment in specific means that you can commit to something, you can hide the value of something, and you can reveal the value of the polynomial later. So this is called opening a commitment. So that the process of hiding your secret in layman's terms would be um, PCS, polynomial commitment scheme, and the interaction part where you ask Bob, "Hey, what just happened to your second hash? Send me your commitments," is the IOP or interactive oracle proof. Now, we don't want to collude with Bob, or we don't want Bob to convince us something which is not obviously the truth. So we try to make it non interactive. And that is why snarks are nothing but succinct, so a short proof, and it is non interactive, so we don't actually interact with Bob. And when does it become ZK? So zero knowledge. It becomes zero knowledge when we don't reveal anything about the commitments or the secrets. So to make it zero knowledge, the commitment scheme has to abide by these true properties, which are hiding and binding. Hiding means that it reveals nothing about the committed polynomial, And binding means that they cannot be like two polynomials which, when committed, produce the same commitment. Or when you open a commitment, there cannot be two valid openings. So this is about just zkSNARKs, and this is not even at the surface of it. So yeah, feel free to dive in and know about this later. Now, yeah, cool. So now we have a bigger problem. Now we're not just dealing with Alice and Bob and their secrets and their small petty issues. Now we're dealing with a bigger problem like so if you're familiar with EVM, you know that every new node has to verify all the transactions done by all the previous nodes. And this is sort of a bigger issue. And what our devs, ZK devs, and the EVM, the blockchain sector thought that it would be a good idea to use zkSNARKs over here and just write a program to get all the transactions. Or this is just an example, this could be applied to anything. So we developed this modern zkSNARK system where you could write a ZK program, feed it into a proof system, and generate a proof. So this proof system that you see is what we had here. So modern snarks have PCS and IOPs. PCS is the polynomial commitment scheme, and IOP is the interactive oracle proofs. And when you combine it, you get a zkSNARK. And that makes up for your proof system. So, uh, yeah, this one, yeah, yeah, yeah. So we had part one where you hide the secret, and part two where you interact and generate a proof saying, oh, yeah, it's true, or if it's no, that's not true. This is actually what a snark is. So a snark just hides whatever witness values you have and generates a proof, a non-interactive way mostly. Um, uh, and this is what snark is. So it's like very simple. A snark could be broken down into PCS and IOP. Yeah. So yeah. So if you've come from a development background like front end, back end, if you understand that, circuit could be called as a front end of the ZK system, and the proof system could be called the back end of the process going on here. So there are a lot of proof systems like Grot16, Flunk. We'll dive into it much later. But for now, we're going to look into circuits. So just to recap, circuit is just a ZK program that you write to generate a proof using a proof system. And that proof system, which uses zkSNARKs, is made up of IOPs and PCS. PCS, we use it to hide values. So these are polynomial commitment schemes. And IOPs are interactive oracle proofs, which obviously interact with the prover and the verifier. They go to and fro to get us the proof. So I hope that's clear, and I'm not like going too fast or too slow. So let's just discard our main characters, Alice and Bob, and get into provers and verifiers. So we're not no longer in with Alice and Bob. Yeah, so our first circuit language is Circom. Many of you would be familiar with this language. It's sort of very a popular language. So Circom takes inputs and outputs, takes input values and generates output signals. So just like um, variables, but not exactly variables, it takes in signals. So you could give A, B, C, anything as input, and you could generate outputs as well. So this circuit over here, which you see on the left, is a very simple circuit. So um, you instantiate the circuit. So you start writing the circuit by using the keyword template, and you have the circuit name. You have signal input A, signal input B, which means that we're going to take two signals, which are inputs, and we're going to get an output signal C. There can be as many inputs and as many outputs as you want. And yeah, the next thing is we are adding A and B, and we are assigning it to C and also constraining it to C. Now, this word constraining, constraints, under constrained is used a lot in the ZK circuit building space. So it just means, yeah, cool, cool. Um, yeah. So you would come across this term constraints a lot. So let's just say constraints are limitations or bounds. So let's say to generate a valid proof, you have to satisfy all the constraints. So if you go back to the Alice and Bob problem, the constraint was that for whichever letter or whichever index Alice says, Bob has to give the correct hash. So it would be hash given by Bob should be equal to hash produced by Alice. That was the constraint there. So here we say that when we do A plus B and assign it to C, it has to be so those two variables have to be equal. So in Circom, there are two operators, which is like a bit confusing. We have the assignment operator over here, and we have like three equals, which actually generates the constraints. And if you just combine these both operators, you get the assignment and the constrainment operator. So I just used that one where you assign and constrain in the same line. So these assignments are done by the prover, and the verifier only calculates the constraints. So if you just use the single arrow where you just assign something, the verifier is not going to see that. So yeah, that's an issue. Um, then the next line, moving to the next line, we created an additional constraint which says that C has to be equal to 77. Now just to sum it up, we have a circuit which takes two inputs. It adds A and B, and it says that the output C has to be equal to a number 77. Now, if you pass the incorrect inputs, such as 7, this circuit would generate the incorrect proof, or this would not go through. So this constraint would fail, and your verifier would not accept your proof. So there are two mainly used tools in for Circom. One is zkRPL. I use it almost every day if I'm coding in Circom. And the other one is Circumscribe. It's a really great tool to visualize all your constraints. So if you just feed this circuit in Circumscribe, it's going to give you this exact output. It says that circuit.A, which means the input of circuit A plus the input of circuit B minus the input of circuit C has to be 0. So that is how it creates constraints and polynomials. So let's dive into zkRPL and see how we run our circuits. So I have my circuit here, and to run this circuit, I just have to do Shift and Enter. And it says I have one linear constraint, which is this one. And I have two wires, four labels, that's all fine. And the output is 77. The C here is 77. Now, if you want to try circumscribe, oh, okay. So I'm using example as the name over here. You can use any name. So that is how you write circum circuits. So I thought it'd be a good idea to go through the process of proof generation and then verifying the proof on chain. And there are two ways to go about it. The first way is to use zkREPL. Yeah. So before that, let's just complete Circom. So yeah, so there are just three types of signals in Circom. One is the input signal, next is the output signal, and you have intermediate signals. So you can just, let's say you want to use signals and somewhere in the middle, you can just create one. And these signals are immutable. So let's say you assign a signal once, you cannot reassign those signals later. And to people coming from FPGA backgrounds or something related to chip building or Verilog, this might be very familiar. There is a concept of variables, but you can like use it to build constraints and not do calculations. And all operations have to be of the form multiplication or addition, and the multiplication has to be non quadratic. Sorry, the multiplication has to be quadratic and not non-quadratic. Now, to people, what is quadratic? Quadratic is nothing but something of degree 2. Linear would be something of degree 1. And non-quadratic will be anything that is not of power 2. So x into x would give you x squared, and this is quadratic. And anything other than this form is not really allowed. So you can use these to assign but not constrain. Yeah, and Circom has a constant computation graph. So if you come from a tensor flow sort of background where you have a static computation graph, you cannot run endless loops or loops of your choice, or the variable computation graph, I would say, like in normal programming. The last point is that the scalar field is around 2 power 254. So this is not the exact number, and why this is important is that the maximum number you can use inside this version of Circom is around 2 power 254. So if you use any variable, any number like 2 power 255, what would happen is that the number used in the calculations would be 2 power 255 modulo 2 power 254. So that's not what you want. And if you want to change this, you can. You can just fork Circom and go and change the scalar field there. Yeah, that is about Circom. And yeah, so there are a few security issues, such as there are going to be malicious provers. So you've got to write sound code or proper code, and do not use the single assignment operator, the single arrow, unless you know what you're doing. And some of the other security issues is that if you leave your inputs unassigned, a malicious prover could insert his or her preferred value and generate a malleable proof. Yeah, and for the issue, I just explained that. So if you use an integer of 2 power 255 bits, this leads to an overflow. Yeah, and always check your bit lengths. And yeah, there are a lot of precautionary measures you would see while using Circom. But yeah, these are some of these. Yeah. So now let's just generate a proof and verify it using a smart contract. So to do this locally in your system using VS Code, you would have to have Circom installed and SNARK.js installed. And if you cannot follow through this video, feel free to check out any of these tutorials by Rare Skills or the other one. They've got like really good tutorials on that. And yeah, all the code that we do is in my repository. So yeah, you could check that out as well. So yeah, a shortcut to do this is to go to zkREPL, and this is how I do it. You can do any of those. You can either generate a proof using ROT16, or you could generate a proof using Plonk. So these are proof systems which you could use. So I'm choosing the Plonk way. Right. So I've got a proving key, a verification key, a solidity file, and an HTML file. And the solidity file is what I want right now. Because, yeah, let's see. Okay, I have to download this. This copy that contract and paste it into my remix. So if you guys can see my screen, I have a Plonk verifier contract. I'm just gonna remove this. So yeah, sure. So as I said, we'll be using multiple proof systems. So if you just got the concept of snarks and proof systems, one of the proof system is Plonk. So Plonk is also the name of the IOP, and the polynomial commitment scheme that we use here is KZG. Um, eh, so let's say you're generating a proof using the Plonk proof system. You would get a verifier generated by the same proof system, and that is what we have here, the Plonk verifier contract. Uh, oh, you could just compile it. Okay, there's some issue. Identifier not found or not unique. What is this issue? Let's just change it to 256. Just deployed that contract, and we have a function over here called verify proof. So what is a proof? I mean, what are we generating a proof for? We're generating a proof to say that we know two inputs, A and B, which when added equates to 77. And we're going to generate the proof using our command line. So we would have a good idea of what snark.js or how or we could use snark.js. So I have over here, can you see my VS Code? Okay. Measures. So yeah, I'm just gonna paste that circuit we just did, and let's just remove this. So there are a few commands. First one is to compile the circuit. I have a cheat sheet ready. So you do Circom circuit. So our file's name is circuit.circom. And I'm gonna open my command line and paste that. Oh shit. Oh, okay. So everything went okay. Circom save. Cool. So the next thing we've got to do is yeah, we could do what we could do is generate an R1CS file. So if we just go back to what we did before, like 10 minutes, we said that the message would be turned into a polynomial. So before turning into a polynomial, Circom circuits would be boiled down to something called R1CS. R1CS is nothing but gates and wires. It's something we'll see later. So um, we could do that. Okay, so we just generated an R1CS file with a .sym file which has all our signals. What else could we do? Okay, if you just click on the R1CS file, it won't be displayed because it's a bunch of binary stuff and not really visible in VS Code. So we could turn into a more readable form. So let's do. So it's using the BN128 curve. It has two wires, one constraints, two private inputs, four labels, one output. Yeah, that's our information about the R1CS file. Uh, the next thing is to turn your file, to generate a JavaScript file to create your witness vector. So go here, paste this. Yeah, we just created a circuit underscore JS file. It has three files. One is to generate your witness vector. You just have to use this command, which I have it over here. But before that, you would have to create an input file to specify your inputs. So if you see here, we just have our circuits and our inputs. There's the values for A and B are nowhere to be found. So what we could do is go and create input.json and specify our inputs in this way, like a JavaScript object. And the next thing is that we have to export this as a witness file. So we have to run this generate witnesses file. So we just copy this command and paste it in our terminal. Our witness file over here. Again, a bunch of binary. Yeah, if you want, we can see the same file in JSON format. So just copy this. I have a JSON file over here. And yeah, coming to the section you've been waiting for is to create a proof. So to create a proof, we're doing it using Plonk, and Plonk does something called universal trusted setup. So Groth16 is another proof system which uses a trusted setup for every circuit. So if you want to generate a proof using Groth16, you have to do a trusted setup for every circuit. But now we're using Plonk, and we just have to do it once, no matter how many circuits you use. So over here, I have a p tau file. Now, p tau stands for powers of tau. I have it over here, and it's 28, so the eighth one, which means that the maximum constraints I could use is 255. So if you just look at the number of constraints we use over here, it's just one. So just look at your circuits, and as per your constraint requirements, you could use the powers of tau file. Yeah, so I just downloaded this powers of tau file earlier, and I'm going to use it to do my trusted setup. Now, why do we need trusted setup and what is all this? Just go back in PCS. What we did was multiply the coefficients of a polynomial with some random element g square. Those g and g square elements come from our this beta of 5. So I have a whole blog written for this, so you could know more about that. Yeah, sure. We'll just paste it here. So we just generated our .z key. This is like a proving key, and you could verify if you have the right proving key using this command. Oh, z key file is not got 16. What did I do? Hmm. Wait. Let's try this one. Okay, this one works. Generating a proof. Okay, witness is over here. We just have to move it here. Cool. So I hope we have proof.json. Oh, okay, we're getting the proof. What's the issue? Right. So we could do two things. So there's our proving key and our verification key. If you want, we could just verify it using our command line, or we could use our deployed contract and verify it using a Solidity contract. So let's just do this one first. Okay, so it gave us okay, which means yeah, you're good. The next thing is generating a Solidity file. So if you just rewind back to 10 minutes, we generated a Solidity file using zkREPL, and we're going to do it again now using our command line. So this is, so we have our Solidity file. Now, we're going to transform our proof, which we have, into a more readable format like an array of UN254 numbers. So we could feed it to our Solidity contract. So it's just messing around with our proof. Yeah, here we go. So if you just, this is our proof, just a bunch of numbers. If you see the last one, it is 0x, a bunch of zeros, and the last thing, the last two letters are 4D. And if I'm not wrong, 4D is 77. And what it's saying is that here's your proof and here's your public output for that circuit. So let's just copy this. Try pasting it in this contract. Why is it not working? There's some error. So let's use this one. Maybe we're using different contracts. Yeah, right. See this contract. Read this one. Oh, okay, wait. So whenever I try to share my entire screen, it just doesn't work. So I try to do it in tabs. Can you see my screen right now? Now? Oh, let's just try to compile. Deploy. Okay. Copy our proof once again. Verify proof. So if you can see, there's a boolean returned saying true. Yeah, so it says that, yeah, you gave us the right inputs and your proof is correct. And so if you're gonna verify anything on chain, you do it this way. You deploy this contract on chain, and no information will be leaked if you want to prove something this way. So yeah, congratulations. You just went through a whole lot of tutorial. Um, yeah, that was Circom and smart contracts. So if we have time, maybe we could look at other proof systems. And yeah, just let me know if I'm taking too much of time.
Have all the time you need, as long as you want to stay. We also have a few questions from our community. One question that I have here from
Oh,
Rookhook is,
mhm.
where is the public inputs that the verifier should take?
I'm sorry. Can you just do that again? Say that again.
Where
Where
is
is the public
yes?
inputs that? Oh, yeah. So if you just look here, where you have your verify proof, and you click on this drop down, you see public signals, and you see proof. So proof is all that uh, huge array from here to here, and public input, public output, which is 77, is what you give your verifier. Say, hey, I got the output. So if I'm not wrong, 4D77, and what you give here in public signals. Yeah, 4D. I hope that's clear. Or oh, cool. Yeah, that was Circom, a lot of smart contracts, Plonk, and zkSNARKs. And just to move forward, yeah. So the ZK circuit development ecosystem is evolving, and we have a few languages. We just had a look at Circom. There's Noir, Socrates, Leo, Cairo, Lurk. So um, most of the time, Socrates is not used. Leo is used by Alio. That's another chain. Cairo, as you know, is Darknet's language. Lurk is used by Lurk Labs, which is like a ZK section of Filecoin. Then you have libraries, the famous Bellman library, Arcworks, and all these libraries, which you could use to write circuits and prove to people whatever you want. And proof systems. So, as I said, we just used Plonk. There are other proof systems like Grot16, Plonky2, and Boojum, which many people will be looking into this week or for the next month, because zkSync uses Boojum, and Boojum is nothing but Plonk IOP with polynomial commitment scheme as Fry. So yeah, so if you want to get into zkSync contest, just go look at Boojum and try building circuits with Boojum. And yeah, obviously look at the EVM structure as well. So yeah, that would be my 2 cents. Um, Moving on. Yeah. So I just mentioned R1CS a while ago that if you have a message and you want to convert it into a polynomial, the first thing it boils down into is R1CS. So if you have a circuit this constant 77. So while building our chip, we could say, yeah, it's going to be 77. We could like enter the value over here. The next is our selector columns, where we specify if the following gate has to be on or off. So mostly the value is 0 or 1. And if you have a gate which defines, oh, A0 plus A1 has to be equal to F1, there has to be a selector over here specifying, oh, you have to do this. You have to perform this operation. So this is about Halo 2. Uh, yeah. So just doing a recap, every column is a polynomial. So all the witness values you have boils down to polynomials. Um, and okay, this is very technical. I shouldn't have done these. Okay. Yeah, and if you want to have a look at the Halo 2 circuits, I have that as well. So let's just close the Circom one and go to Halo 2. Yeah, so this Halo 2 library, which I'm using, has been developed by the Zcash team. And yeah, you just have to import their library and define columns. So this might be a bit buggy because I didn't check it. So let's say you want to have your input A and then your input B. These two inputs come under the advice column. If you just recall, advice column is where your private inputs come under. So yeah, so column A and B is for that. Then you have your selector and instance columns. Then you create a chip and you create a gate saying, oh, I want an addition gate. And what I want to do is I want to add A and B and the output, which is C. So when you do A plus B minus C, it has to be 0. So we create a constraint this way, and we sort of use our layouter to assign. I'm not going too deep into this because, yeah, it would take a lot of time. But feel free to just come in and check this. So yeah, this is how you create a circuit using Halo 2, which is another library. The third one is Noir. Noir was developed by the Aztec team, and Noir is still under development. And they have this. Out of all these, I would say this is like most easiest language to start your circuit development journey. It's very much like Rust. You have to define. It's very much like a normal program or how you write a normal script. So I just do the same circuit in all the proof systems, all the circuit building tools. So here we take, yeah, yeah. These are on my GitHub. Yeah. Yeah. So we're doing the same thing, adding A and B and saying it has to be equal to 77 and returning C. So in Noir, all the outputs have to be public. and you specify that keyword, or else it would give you like an error if you don't specify this. There's missing pub keyword. So yeah, and I just wrote a small test to see if it indeed passes. And if you just check the directory structure of Noir, there is the Nargo file where you have just basic information, and then you have your prover file where you specify your inputs. So A and B, I'm giving here as 4 and 73. And the verifier file, because we say that C has to be equal to 77. Oh my god, too many files. Um, So yeah, that's your verifier dot toml, and this is your prover dot toml, and you give your inputs to the prover. So try to run this. So the last time I tried to run, it just got stuck, and it was like this for like 2 days. There's some issue with Noir since they're actively developing it. So yeah, Noir tests. So Nargo tests run well. Yeah, it says all tests passed, verified to Nargo proof, which is the command you do, you give to generate a proof. It just gets stuck. So yeah, just try it some other day. It's very easy and very um yeah, very easy for beginners, I would say. And here's my Noir cheat sheet. Just like a few instructions or commands that you could use to generate proofs, verify those proofs, compile circuits, see, initiate a new project, or just like in Long, where just like in SNARK.js and Circom, where we created a Solidity smart contract to verify that we have the right proof, you can create a verifier contract in Noir, and the command for that is nargo codegen verifier. So yeah, just try these out, and it's going to be very easy with Noir. Uh, Coming to our last section, which is Plonky 2. Again, just going to go over the same one. So Plonky 2 is a bit different from the other circuit systems, and Plonky 2 is very similar to Boojum, I would say. Though I haven't looked at the ZK, PCS and IOP. They just have different names in my head. So Plonky 2 uses FRI as their PCS, polynomial commitment scheme, and Plonk as its IOP, and it operates over the Goldilocks field. So if I'm not wrong, Goldilocks field is something like 2 power 64 minus 2 power, what is 2 plus 1. This is the Goldilocks field. And this is a small field, so the proof generation and verification is very fast. And there are not many applications or circuits using this. So if you just search over GitHub, you wouldn't find many full blown applications. Though Mir Protocol or Polygon Zero uses this. But yeah, it's evolving, and many folks are building over it, such as Sysync Labs. Um, they are building a wrapper called Plant. Um, yeah, again, very similar to Halo 2. If you go through Halo 2, you would find that there is this circuit config. You initialize a new circuit, and you get a builder object, and you add labels. Here, the labels are called targets. So you say, oh, I have an input A, I have an input B, and there's going to be a label C as well. And you add it and you try to create constraints. So yeah, that's how Plunky 2 works. The one thing which separates Plunky 2 from the other ones is that the verification is also done inside the circuit. So it uses recursion. So to just explain it in a simpler way, you have your circuit, you generate a proof saying you had your, yeah, you computed the values in a correct way, and you have a verifier inside the circuit, and you feed that proof to that verifier inside the circuit, and you generate another proof. So here what you see is called recursion of proofs. So this way you get a proof size and the verification cost and the proof cost is like lesser compared to other circuit libraries. So yeah, we just covered like four, two languages and two libraries.
I gotta say, this is very
It's a full
cool.
blown.
A very cool presentation. Thank you so much, for doing that for us. Very enlightening, and to see all the different applications, to different languages, also very important. I have a few questions from.
Mhm.
By the way, keep going. I think you still have slides.
Uh, no, I just have resources. So if you want
Awesome.
to get started with Circom, just go ahead, Noir, Plunk, more Plunk, Halo 2, Plunky 2. Yeah, that's it.
Are you making these presentation available so we can click on these links?
Yeah, sure, sure. Why not? Yeah.
Thank you so much. I have a few
Mm,
questions here from community. The first question, actually,
okay.
you just answered one. I think is ZKEVM and zkSync similar? If we are familiar with the ZKEVM workflow, can we participate in the zkSync contest, or we need more info on zkSync only?
Nice question. I've been getting that question a lot today. So there are multiple types of ZKEVM. If you're familiar with Tycho, Scroll, or the ZKEVM which PSC is building, so yeah, there are multiple approaches to build zkVM, and zkSync is just one of those zkVM. So if you're familiar with EVM itself or how opcodes and read-write operations work in EVM, I think you'd be good to go with the zkSync contest, because what zkSync has done is that they've created a zkVM very similar to our AVM, and they might not support a few opcodes or they might not support a few operations. But if you know EVM well, you would do good. Yeah.
Awesome, awesome answer. How does the concept of universal setup in zkSNARKs impact the security and applicability in real-world scenarios?
Really good question. So, if you just go back to polynomial commitment schemes, which I find over here, you see G square, G cube. These are supposed to be kept secrets. Like when a trusted setup happens, I'm sure you might have seen a lot of tweets saying participate in this trusted setup. And what you do is everybody comes together to contribute randomness, and a random set of points are generated and used in generating the commitments. So, in terms of security, let's say we all of us reveal our randomness, or somehow these random parameters are compromised and gets into the hands of some bad person. That person could use the secret information to exploit um, the proof or generate malleable proof. So it's extremely important that we try to randomize our trusted setup process as much as possible. So one of the very famous trusted setup process, which just got closed like a week ago, was the KZG process from Ethereum. Not familiar if you guys participated in that. Yeah.
Nullity, I think this is it. This was really enlightening. Thank you so much for this presentation. I wanted to know if you have any closing thoughts or any message you want to leave for people that will see this in the future.
um, I would say just participate more in such budding technologies like trusted setups, or show your support for people who are building these ZKVMs. They are working really hard, and if you're interested in learning, yeah, do give it a try.